Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So in our last class we started the chemistry of p block elements, and in p block what we have seen mostly is initially that this region of the periodic table, this portion is called p block elements. And p block elements, why they are p block elements? It is defined the last electron while writing electronic configuration fall in p orbital. And so we have also seen that this block means the p block contains, this is the only block in the entire periodic table, or the only portion of the periodic table which contains all metals, non-metals and metalloids. And so I also said that if you draw just a diagonal line between boron and astatine like this line, diagonal line, the elements which fall near this diagonal line, they are metalloids. Elements below this are metals, and above this are, or right side to this line, are non-metals. So only few non-metals are known to us, uh, and then we show some other things. What are the different groups and the group names as well. So this boron family, the common name is also trial because it mostly forms trivalent compounds. If the compounds are covalent in nature, so trial, this is tetrail group. Or the carbon family we call boron family, carbon family, nitrogen family you also call nitrogen family, oxygen family you also call chalcogen family, fluorine family is also called most commonly halogen family, and this is the noble gas series, a noble gas group. These things we have already seen. Then we also saw the general electronic configuration of all the groups that belong to P block of the periodic table. The NS2 NP126. So NS2 NP1, it starts for the group 13 and it goes to NS2 NP6. So general electronic configuration we can write for the P block elements as NS2 NP126. And then we started that we saw many other things. Then we started boron family and basically chemistry of boron family and what are the boron family members. We know the boron, aluminium, gallium, indium, thallium and nihonium. About nihonium we saw that I explained that it's the most stable isotope of nihonium, has half life only up to 20 seconds. So you can see 20 seconds is nothing time, because you cannot perform chemical reactions in between this a small uh, fraction of time. So what happens if chemistry of nihonium is not known to us? Why again, the most stable isotope itself has half life only 20 seconds. So how, what kind of chemical reactions we will perform in 20 seconds or something like this? So it is very unknown, very, and other group chemistry that we know that we have seen, and that is our focus will be. So we started the electronic configuration. Then electronic configuration, few basic points I explained, and the basic point for the group 13 elements, what we know, the general electronic configuration NS2 NP1. And here the boron and aluminium have noble gas core. This is important. So boron and aluminium, if you see the electronic configuration, boron helium 2s2 2p1 and aluminium neon, electronic configuration of neon 3s2 3p1. So what we see, the core, this is the valence shell electron. So valence shell, this belongs to valence shell, and whatever the core is the noble gas core. So for boron and aluminium, however, when you come to gallium, what we see, a core of argon, which atomic number is 18, and then 3d10 and 4s2 4p1. So 3d10 also belongs to the core electron, because this is the 3d electrons, the valence electrons. Sometimes these electrons also take part is for the d block elements, particularly in the reactions. But what we see, this is also part of the core electron. So 4s2 4p1 is the valence electron, and this is the, so core of the gallium contains argon, the core of argon plus 3d10. So whatever the electronic configuration of argon is, you have to write that electronic configuration, then 3d10, and then finally the electronic configuration of the valence shell. And similar thing we see for the indium as well. So in indium, only the difference is the instead of argon here, the krypton, the core of krypton will be there. So this kind of things we saw. The gallium and indium have noble gas plus 10 d electron core. So we see noble gas plus 10d electron core. When you go to thallium, what we see, electrons will also go into 4f orbitals. So 4f orbitals, and for nihonium as well, electrons will go in 5f orbitals. So the core will contain core of xenon plus 4f14 plus 5d10 for thallium and nihonium. The electronic configuration of radon or the core radon core plus 5f14 plus 6d10. This is all the core of these elements. This is what we have explained as well. So now the atomic size, I am just repeating it because these are important points. Atomic size, when we go down the period, usually what we have read in the periodic trend, that atomic radius increases. Generally, it increases as you go down the group. However, we see one exception, one reversal between aluminium and gallium. Gallium's atomic radius is smaller than aluminium, and the numerical value you can see. Gallium is 135 picometer, means 1.35 angstrom, the radius, atomic radius of gallium, and for aluminium it is 1.43 angstrom or the 143 picometer. It means gallium atomic size is smaller than aluminium, and the reason we have seen, we have cited, is the d block contraction, because after aluminium, when you go to the next group, you see that the electrons will also go to 3d orbitals, and 10 electrons will go to 3d orbitals, so 10 protons will go to the nucleus. And these d orbitals, electrons in d orbitals do not have that much screening effect, so the effective nuclear charge increases. Because of increase in effective nuclear charge, we see atomic radius of gallium is smaller than that of aluminium. Then we see there is a very slight change in gallium and aluminium, and slight increase we see further. So ionization enthalpy, most of the things you might remember. The only thing is the first ionization enthalpy is always smaller than the second ionization enthalpy, which is smaller than the third ionization enthalpy, and this is general for any element. Coming to the electronegativity, and what we saw there as well, we do not see any concrete trend in the ionization enthalpy as we go down the group. So, and electronegativity, what we see, and we know boron is not a metal. And if you go to after boron, aluminium, gallium, indium, selenium, they are all metals. So from boron to aluminium, the electronegativity decreases, and but after aluminium, it increases slightly. And you see in the Pauling scale, it increases by 0.1 as you go from aluminium to thallium. So this is very easy to remember electronegativity as well. Boron, you can remember 2.0, and then 0.5 decrease to aluminium, and then slightly increase by 1.1 on the Pauling scale. And then we show the physical properties, particularly boron. What we saw, it exists in many allotropic forms, and it forms a very strong crystalline lattice. And because of the formation of very strong crystalline lattice, its melting and boiling point is highest in the group, because it is very difficult to break that crystalline lattice to make this boron crystals melt or even go to evaporation. So we need to provide more energy, high energy, so its melting and boiling point is highest in the group. Rest of the members are soft metals with low melting point and high electrical conductivity, as they are metals. And what we see, the gallium's melting point is lowest in the group. And so gallium, you see the melting point is 303 Kelvin. 303 Kelvin means in the summer it will be in the molten form, in the liquid form. Unlike the ghee that we see, ghee, vanaspatis, and many other nariyal, coconut oil. So its behavior will be like that. In winter, it will be in the frozen form and in the solid state, and in the uh, summer, it will be in the liquid state. And the density of these elements increases down the group from boron to thallium. So this is, there is one general trend in density. The density always increases from boron to thallium. So this thing you should remember, wherever there is a concrete general trend, you should always remember the density has certain order, is change in the order. So density follows certain order, and you see the values of density. The boron density of boron is 2.35, and in the gram per ml per cubic centimeter gram cc. So 2.35, then aluminium 2.70, gallium 5.9, indium 7.31, and thallium 11.8. Final, you see that density increase. In a region of increasing density is that we know the atoms are becomes heavier, but their size doesn't increases in the same manner, and so the size is increasing, though it is increasing with certain exception here. So size is increasing, but size is increasing, but uh, this mass is increasing more, and so density increases, because density we know it's mass divided by volume. And so if the atomic number of these elements you perhaps know, 5 for boron, aluminum 13, gallium 31, and indium 49, and thallium 81, and this kind of thing. What we see here 13 to this 81. So this, sorry, 31, 81. This thing what we see, the usually for the all the element in the P block, what you see here, just want to know, tell you some certain trick to remember the atomic number. So 31, one period is in between C plus 50, the thallium 81, germanium 32, so this lead is 82, 33, 83. And when you compare this period, aluminium, silicon, phosphorus, from there to nihonium, this period, what you see, there is increase of 100. So here to here, increase of 100. Silicon 14 to flerovium, 114 atomic number. This phosphorus 15 to moscovium, 115. So you see there is an increase of 100 from here to here. So in between there are three periods. So if there is one, so this period you can consider as the middle one, and aluminium, and this trend you can just see the symmetry is there. So from here to here, difference of 50, here to here difference of 100. So some kind of symmetry is there. And so our other way, and atomic masses is given, and you can see the mass, atomic mass is average. This is average atomic mass, it increases, and we see it increases significantly. And also we know that because if atomic number is increasing, similarly that means the number of protons in the nucleus is increasing, and in the similar proportion the number of neutrons in nucleus will also increase, and so the atomic mass will also increase. Electronic configuration I have already explained. Atomic radius we have seen, so just see the values. So atomic radius of boron 88 picometer, aluminum 143, gallium 135, and then from gallium to here we see 167 indium, and one indium, from indium to thallium 170. There's just a slight increase here. So this is the atomic ionic radius. However, what we see, there is a distinct trend in the ionic radii of this elements, and ionic radii plus 3 in the plus 3 oxidation state. If you look, so 27 angstrom for the aluminum 3, sorry, boron 3 plus. Although this is boron doesn't exist in plus 3 as plus 3 ions, so that this value is somehow it's a very unstable state. The general trend you can see the real value from here to here. This is just a predicted value. So here as well the predicted value you can consider. So this is the real value, the experimental value. So 53.5 for aluminum 3 plus, then gallium 3 plus 62, then iridium 80, 88.5. So you can see here the continuous increase in the ionic radius when the ion is in plus 3 oxidation state, or ion is the tripositive ion. So tripositive ion is 3 plus charge on the ion or the element. The ionic radius when ion has plus 1 charge only, so here these two do not doesn't form plus 1 ion. However, the gallium plus 1 ion can be seen for the gallium, indium, and thallium, and this is because of the inert pair effect. Here again for these three elements what we see, there is an increase in the ionic radius as we go down the group. So ionization enthalpy, you can see there is no clear trend from here to here, decreases, then increases, then decreases, then increases. First ionization, second sub. What is important to remember here is if you sum these values, so you see these values are very high for the boron, and that is why boron doesn't exist in plus 3 as a plus 3 ion, because if you sum all these three values it will be quite high, so energetically formation of boron plus 3 is very unfavorable. and for other cases the values are smaller, and that much value can be compensated with the hydration and other further reactions that you see here. Next, maybe the crystal, the lattice energy or the hydration energy if the ion is in the aqueous solution. However, this value, some of these values are not compensated because of the hydration or the lattice energy, and so boron doesn't form plus 3 ion. Electronegativity, this value we have already seen. Density we have seen. Melting point, if you see the melting point, boron, as I said, it has highest melting point. So melting point, it decreases from boron, aluminum, then gallium, and then it starts increasing. So from gallium, it increases. So gallium has lowest melting point in the entire group. And the boiling point, if you look, boiling point of boron is also highest, then it decreases, continuously decreases. So boiling point continuously decreases as you go down the group. However, the melting point, there is a first decrease up to gallium, and then an increase is observed. If you look at the standard reduction potential for metal plus 3 ions going to metal, the neutral metal or the solid metal or the solid element, for the boron, this thing plus 3 ion formation is not possible, as we have seen. Even plus 1 ion formation, boron doesn't form ionic compounds. So this is not possible, because even though first ionization energy for boron is very less, but accordingly there is only one charge plus charge on this. So the ion that will form boron plus 1 ion, that will not get stability because of the hydration. Hydration energy will also be very less. And so if you look at the standard reduction potential for metal 3 plus to M, what we see, the negative value for aluminium, it does, what does it mean? It means that the reduction of aluminium 3 plus in the aqueous solution is not that facile, it is not spontaneous on its own, because this value is negative, and what we know, delta G is equal to minus NFE. So delta G will become minus, sign is already there in the formula, and the value of E naught, if you put as negative, it will become positive. Delta G will become positive. It means that formation of M3 plus, means aluminium 3 plus to M, is not feasible thermodynamically. It's not a spontaneous reaction. Similar value we see for the gallium. However, spontaneity, this value, in the positive, the value for delta G will decrease. So delta G positive value will decrease. So it has a better prospect comparison to the aluminium. Then indium, we see again the negative value. It also doesn't favor that reaction. Non-spontaneous reaction from M3 to M plus. It means M to M3 plus will be spontaneous. However, when we look at the thallium, we see there is a positive value for delta E naught. Positive value for E naught, it means that the reaction in this direction is spontaneous, means M3 plus to M formation is feasible in this case thermodynamically. And so delta G value will be negative minus NFE. So N, value of N, how many electrons are taking part in this reaction? 3 electrons. So value of N will be 3. F is Faraday's constant, and we know it's about 96,500, and E naught is what? 1.26. So delta G value, not value, you can easily compute from this equation here. And it means the reduction of thallium 3 plus to thallium metal is possible, and that is thermodynamically feasible process or a spontaneous process. It means thallium plus 3 oxidation state is not a stable state. It means thallium usually do not prefer to be found in plus 3 oxidation state. However, if you look at the thallium, the standard reduction potential for thallium plus 1 to thallium, you see this value is negative. It means that thallium can exist in plus 1 oxidation state. Means this reaction in the opposite direction will be feasible. M plus to M is not feasible, but in opposite direction, M to M plus, it will be feasible, and that will, this sign will become positive. It means thallium can exist in plus 1 oxidation state or plus 1 ion, and it doesn't exist, it doesn't prefer to exist in as plus 3 ion. And if it doesn't exist as plus 3 ions, thermodynamic stability is not there plus for thallium plus 3 ions. It means if thallium plus 3 is there, it will try to convert into thallium plus 1, because thallium plus 1 is even more stable, thermodynamically more stable than thallium 0. That is why it is going in the reverse direction if the medium is aqueous medium. And so thallium 3 plus it reduces, so it will oxidize other. So thallium 3 plus or thallium in plus 3 oxidation state. For example, TlCl3, it behaves as oxidizing agent. So this is a very important point. So thallium 3 plus is an oxidizing agent. The reason is this. And why thallium plus 1 is stable and thallium 3 plus is not stable? The reason we cite is the inert pair effect. An inert pair effect is what? Because of the, as you go down the group, penetration power the F of the s orbital increases, and because of the penetration power of the s orbitals are now nearer to the nucleus, so removing the electron from the s orbital is difficult. And the example that we see here, when as we start the electronic writing electronic configuration, electrons are put first into 4s orbital, then the 3d orbital, and electrons are being put into 5s orbital, even being electron putting into the 4d or even the, or the 6s orbitals, even putting electron in 5d or 4f. It means the electrons, this 6s is nearer to the nucleus than 4f and 5p. And that is what the one example, this penetration power as you go down the grip increases of s orbital increases. It means s orbital with its electron is nearer to the nucleus, and so removing that electron is not that feasible, that not that easy. And so because of that we see the inert pair effect for thallium. And plus 1 to metal, this reduction, what we see, this reduction is not very feasible. For this reduction is feasible for aluminium. If this value is possible, means aluminium forming aluminium plus 1 ion is very difficult. And so for the gallium, we see this is a negative for this acid and alkali both. Now let us look into the chemical properties. So one of the chemical properties we have already seen, this reduction potential, that is also a chemical property. Rest of the things we have seen were all the physical properties. Now let's look into the oxidation state and trends in chemical reactivity. So what we see, boron doesn't form plus 3 ion, as I have said earlier. Due to why it doesn't form? Due to its small size, the sum of first 3 ionization enthalpies are very high. Thus, boron forms only covalent compounds. And aluminium is highly electropositive metal. This we know. It loses electrons and forms plus 3 ions because the sum of first 3 ionization enthalpies of aluminium decreases considerably if you compare with the boron. For gallium, indium, and thallium, both plus 1 and plus 3 oxidation states are observed. We have seen it in previous table. And that is here, plus 3 oxidation, plus 1 and plus 3 oxidation state. For gallium, indium, and thallium, we see the compounds there. So all the gallium, iridium, and thallium, they were found there in plus 1 and plus 3 oxidation state. However, the relative stability of plus 1 oxidation state progressively increases for heavier elements. So plus 1 oxidation state will progressively increase, means the thallium plus 1 oxidation state is more stable than indium plus 1 oxidation state. Indium in plus 1 oxidation state will be more stable than gallium in plus 1 oxidation state. This is relative terminology. However, if you look at the overall stability of plus 1 oxidation, you will see only thallium is stable in plus 1 oxidation state. None other element is stable in plus 1 oxidation. So you can see not this possibilities even for this as well. The iridium, so thallium it is more stable, and iridium it possibility is also there. From the reduction potential value, you can just make it out. This value, if you remember, delta G is equal to minus NFE. And why this relative stability of plus 1 oxidation state progressively increases for heavier elements? The reason is due to poor shielding effect of intervening d electrons and f electrons. And the reason the penetration I said, and this why this penetration, these d and f orbitals are farther from the nucleus, and so their shielding effect will also be poor. And it means their penetration power is lower than s and p orbitals. The increased effective nuclear charge holds ns electrons tightly. So ns electrons, why it holds tightly? Because it goes closer to the nucleus, and that we call the penetration power, are responsible for the inert pair effect, and thereby restricting their participation in bonding. and so ns electron do not take part. If you go down the group, their participation in the reaction decreases as you go down the group. As a result, only p orbital electrons take part in the bonding, and so p electrons will take part in the bonding. And p has, for the group 13 elements, p orbital has only one electron, so the only one electron will take part in bonding, means plus one oxidation state, because all of them are metals. Heavy elements are metal from aluminum to thallium, so they will form plus one oxidation state. So due to inert pair effect, plus one oxidation state is predominant in thallium. So thallium mostly exists in plus one oxidation state. So plus one oxidation state for thallium is the only stable oxidation state. You can form thallium plus 3 compound as well, but that compound will not be very stable, and so that compound will behave as oxidizing agent or the oxidant, and it will reduce to plus one oxidation state or thallium plus 1. The compounds in plus 1 oxidation state are more ionic than those in plus 3 oxidation state, and the reason is very obvious. First of all, if a compound is in plus 1 oxidation state, you have to provide lesser amount of energy to ionize only one electron than to ionize 3 electrons. So that the feasibility energetic from the energetic viewpoint. Another point is the Fajang's rule. If the compound is in plus 3 oxidation state or plus it exists as plus 3 ions, what will happen? So its polarizing power will be more. The charge to radius ratio will be small, and so it will polarize the electron cloud of anions. And because of the larger polarization of electron cloud of anions, so that electron cloud will be shifting between these two ions, cation and anion, and so a strong covalent character will appear, because plus 3 oxidation state is a very high oxidation state, and thus these compounds will have the covalent character. So the plus 1 oxidation state, if the compound is in plus 1 oxidation state and plus 3 oxidation state, if the question is asked which one will have more ionic character, you should always opt for plus 1 oxidation state because of the Fajang's rule. So these elements have only 3 electrons in their outermost shell, that we know, outermost shell NH2, NP1. So 3 electrons in the outermost shell, and if all the 3 electrons take part in covalent bonding, and that we call the trivalent state, if all the 3 electrons are being shared with different elements, so we found the covalent compound, and plus 3 oxidation state, the formation of covalent compound is more feasible, and that we know because of the Fajang's rule and also the from the energetic viewpoint. So in the trivalent state, the number of electrons around the central atom in a molecule of the compound of these elements will be only 6. So this we call the sextet state. And only 6 electrons, the example is BF3 or AlCl3. So aluminum has only 3 electrons, and it shares these 3 electrons with 3 chlorine atoms, and so it will get only 6 electrons in outermost cells. BF3 also, boron has only 3 electrons, and it shares its 3 electrons with the 3 fluorine atoms, which provide only 1 electron to boron. So the total electrons in BF3 will be also 6. And what we know generally for the group second element, or the group third, sorry, period, the second period element or the third period elements, usually they prefer to the second period, so obviously they follow octet rule. But even the third period elements, they have have a slightly stronger tendency to be closer to forming octets. So BF3, if the sextet is there for period 2 or the second period elements, they will follow octet rule strictly. It means if the 6 electrons are there, only one orbital will still be empty. One p orbital will be empty at least for the second period, and the third period elements, one p orbital and the d orbitals will also be empty. And in such a case, if the orbitals are empty, these elements behave as Lewis acid, because if the electron rich species come, so maybe having lone pair of electrons or the anionic charge, so it can donate its electron to the vacant orbital, and so, and that electron rich species called the Lewis base. Electron deficient species or the species having vacant orbital, they are called Lewis acid. So such electron deficient, so only 6 electrons, these elements are electron deficient, these compounds are electron deficient in trivalent state, and so such molecules have tendency to accept a pair of electrons to achieve a stable electronic configuration, and thus they behave as Lewis acids. And this is what the tendency to behave as Lewis acid decreases with increase in the size, and that is because if you look at the base, and if the central atom is larger in size, and that orbital overlap is not that stable, not that facile, and so this Lewis acid tendency decreases down the group. This point is important. So acidity Lewis acid behavior, it decreases down the group. And so BCl3, for example, in the Lewis acid behavior, if you look at BCl3 like BF3, if you just in the place of fluorine, if you have chlorine, so BCl3, it reacts with ammonia. It actually form an adduct with ammonia, and this ammonia has a lone pair of electron. Boron has an empty orbital and p orbital. So ammonia will put it electrons in the empty p orbital of BCl3, and so an adduct will be formed. And this adduct is like this. So BCl3 NH3. Now this compound earlier was planar, it's a trigonal planar structure. But once the ammonia comes, so it pushes these three chlorine BCl bonds and form tetrahedral structure. Now this compound is a tetrahedral compound. Similarly, if the BH3 is there, NH3 and BH3, so NH3, if all the chlorines are hydrogen, BH3, so NH3 BH3 is called ammonia borane. It's found in solid state, so it will also have ammonia borane, will also have the tetrahedral structure similar to the structure that we see for the BCl3 ammonia adduct. Similarly, ammonia BH3 adduct will also, ammonia and borane adduct will also have the similar structure. AlCl3, if you look at AlCl3, it also has aluminum, has only, in the AlCl3 has only 6 electrons, because as I said, 3 electrons of aluminum is shared with 3 chlorine atoms, which also, or each atom shares only 1 electron, so aluminum overall gets 6 electrons, so it has still one empty p orbital. And with the aluminum, another thing, it also has d orbitals, empty d orbitals. So what happens, the two aluminum chloride AlCl3 comes together and it forms dimer. And because of the formation of dimer, aluminum tetrachloride AlCl3 gets certain stability. So one lone pair of the Cl minus, each Cl in AlCl3, each Cl has 3 lone pair of electrons. You can easily understand, because chlorine has 7 electrons, 1 electron it is sharing with the aluminum. So left over is the 6 electrons, and 6 electrons is the 3 lone pair of electrons. And out of those 3 lone pairs, one lone pair it can provide, it can push to the empty p orbital of aluminum, and thus, this AlCl3 unit, one of the chlorine may put its electron or maybe share its electron with the empty p orbital, make an overlap, and this aluminum chlorine is putting its electron in the empty p orbital of this aluminum, so AlCl2 formation will be there. In this compound, some very logical things are there. If I say what will be the, if I say which of the bond, AlCl bond, will be larger in size. So this one can simply understand AlCl terminal bonds will be smaller in size and the middle one will be larger in size, because this chlorine is sharing its electron density electrons with this aluminum as well. And so this chlorine is actually pulled between two aluminum atoms. This chlorine is also pulled between, shared between two aluminum atoms. And so because of the pulling, there was initially force in this direction if AlCl3 is there. For this, the force is only along this direction, but for this chlorine, there is also force along this direction. This way you can understand. So force one component is along this line, so this bond will be elongated. And thus what we see, this aluminum fluorine terminal bond around 2.06 angstrom, and the aluminum fluorine, the middle bond 2.21 angstrom. And the angle, if you look at this CL angle is 118 degree. Ideally in AlCl3 that angle should be 120, but here this angle is decreased because of the formation of the dimer. So another chlorine comes, this angle is only 79 degree, and so this pushes this chlorine and its lone pair pushes these two bonds closer, and so there is a decrease in the angle from 120 degree to 118 degree. And this structure is also tetrahedral, although not the perfect tetrahedral, because why perfect, not perfect tetrahedral? Because in the perfect tetrahedral, what we see, all the angles are of the same value. It is around 109 degree. However, here we see this angle is 79 degree, this angle is 118 degree. And so this is not a perfect tetrahedral, although it's a tetrahedral structure. In a trivalent state, most of the compounds being covalent are hydrolyzed in water. So the in the trivalent state, AlCl3 or BCl3, BF3, these compounds means or TlCl3, TlBr3 or the iridium Br3, iridium AF3. So all these compounds they are trivalent and trivalent compounds. So they have covalent character because the trivalent metal is in +3 oxidation state. So compound will have a covalent character, strong covalent character. So they react with when they are dissolved in water. So they hydrolyze. So they undergo hydrolysis by the water, and what we see the trichloride on hydrolysis in water forms tetrahedral MOH4 species. So, on the hydrolysis, what happens? The OH water molecules are there, water molecules, and being this element, this AlCl3, I am saying some empty orbital is there. One water will go and it will kick out one chlorine. Then another water will go, it will kick out another chlorine, and there will still, if the three water molecules come and H plus ion is going with the chlorine to form HCl. So still there is one empty orbital and the extra water molecule will go and H plus ion will be removed. Finally, MOH4 minus species will be formed, and MOH minus 4 species will be formed that we call the because of the hydrolysis. It means H plus ion, one H plus ion is extra being removed, and that's why this solution will become acidic in nature. So this, for example, this trichlorides on hydrolysis in water forms tetrahedral MOH4 minus species. The hybridization state of metal in this species is sp3. That is very obvious. If you remember the VSEPR theorem, the valence bond theory that I explained. So this is sp3 hybridization will be there for the central atom. AlCl3 in acidic aqueous solution forms octahedral. For the example that we see, AlCl3 doesn't stop at AlOH4 minus state only, or it forms this kind of thing. Another kind of complexation that we see for the aluminium is that all the aluminium molecules, 6 water molecules goes and it forms a complex in the first hydration cell itself. So 6 water molecules will form a octahedral complex with the aluminium, and that bond length is around 1.6 to 1.61 to 1.63 angstrom. So all the aluminium and the 6 electrons will be there, and the water molecules will also be arranged in the second hydration cell. So in this complex ions, what you see, aluminium 6 water molecules forming a complex with aluminium, water, the oxygen has lone pair, it will provide its lone pair to the empty orbital of aluminium in octahedral symmetry. Octahedral complex will be formed. So in this complex ion, the 3d orbital of aluminium are involved, and the hybridization state of aluminium is sp3d2. Why? Because aluminium, if you consider the valence shell electrons, so 3s2 and 3p1 that we know. But the thing is, it with the S and P only 4 orbitals are there, so it can have only 4 bonds. But what we see here, the 6 bonds or the 6 complex, the 6 ligands, as water has 6 ligands. So the 6 electrons, so it needs extra orbitals, empty orbitals, and we know for the third period we have additional 3d vacant orbitals. So the aluminum uses that vacant d orbitals as well here. So hybridization of aluminum in this complex will be sp3d2, means the 2d orbitals are also taking part in this hybridization, and so those orbitals are there and they will be available for forming this compound. Let us now take this question. So standard electrode potential values E naught for aluminium 3 plus 2 aluminium is minus 1.66 volt. This value we have seen in the previous table as well. And that for thallium 3 plus 2 thallium is plus 1.26 volt. Predict about the formation of M3 plus ion solution and compare the electropositive character of the two metals. So we have to compare the electropositive character of the two metals, and we also have to predict which of the plus 3 ions will be formed into the aqueous solution. The formula what we know, delta G is equal to NFE. So suppose this E naught value is given for if the 3 electrons are provided to aluminum 3 plus to form Al. What we see, E naught value is minus 1.66. So delta G is equal to minus NAP. So delta G will become minus 3 into Faraday's constant 96,500 into minus 1.6. So overall value will become positive, and overall value will become positive. It means that aluminium reduction of aluminium from 3 plus to aluminium is not feasible, that is not spontaneous. And if reaction in from aluminium 3 plus to aluminium aqueous solution is not spontaneous, it means reaction in the opposite direction will be spontaneous, and thus aluminium to aluminium 3 plus formation is feasible in aqueous solution, and thus this aluminium 3 plus ion will be formed in aqueous solution. Now let us look at this, compare this value, the thallium 3 plus to thallium 0. This value delta, this E naught value standard reduction potential is plus 1.26 volt. It means the thallium 3 plus will be reduced to thallium, and this direction the minus NFE, this value will be negative. It means in the opposite direction value will be positive. So formation of thallium 3 plus to thallium is not feasible. Is not feasible thermodynamically, means the reaction is non-spontaneous in the opposite direction. So thallium 3 plus ion will be not formed in aqueous solution. So this explanation is given, and what we have to compare the electropositive character of these two metals. And if you look at the electropositive character, one can consider that aluminum has a more electropositive character than the thallium. So thallium plus 1 is more stable in solution than thallium 3 plus. Aluminum being able to form plus 3 ions easily is more electropositive than thallium. This is what we can get from the given data. Now let us look at the reactivity towards air. And boron is unreactive in crystalline forms, and that we know this crystalline forms, the crystal is very stable, and to break that stable form reaction with the air of oxygen is not that feasible. However, amorphous boron reacts with oxygen. So, but in the crystalline form, boron doesn't react with oxygen. Aluminium forms a very thin oxide layer on the surface, and that it becomes aluminium becomes blackish, that you might have seen, which protect the metal from further attack, and so aluminium will be protected because of the formation of oxide itself. So amorphous boron and aluminium metal on heating in air, when they are amorphous boron is heated in air, or the aluminium metal is heated in air, they form B2O3 and Al2O3 respectively. And aluminium, we know the ore of aluminium, exists the more prominent ore of the aluminium from where aluminium is extracted is alumina, which is aluminium oxide Al2O3 plus certain water molecules, is water crystallization also. So what we see, a general reaction of this group elements with oxygen, 2E plus 3O2 gives 2E2O3. And why is this O3? Because they can form plus 3 exist in plus 3 oxidation state. Plus 3 oxidation state doesn't mean plus 3 ion. Please remember, plus 3 ion is different, plus 3 oxidation state is different. HCl, hydrogen is in plus 1 oxidation state, but HCl in the gaseous state, hydrogen is what? In plus 1 oxidation state. It doesn't mean in the gaseous HCl hydrogen exists as H plus ion. Hydrogen HCl provides H plus ion only in the aqueous solution. With a dinitrogen at high temperature, they also form nitride. So all the group elements, when they react with the nitrogen also has 3 valence, 3 nitride, 3 minus, and these group elements will form compounds. So plus 3 oxidation state. So plus 3 and minus 3, so they will form En type of compound. So 2En. Here E is the group 13 elements. Here also E is group 13 element. The nature of these oxides varies down the group. Boron trioxide is acidic and reacts with the basic metallic oxides, forming metal borates. So boron oxide is acidic, so it will only react with the bases. It will not react with acid. Aluminium and gallium oxides are amphoteric, and when they are amphoteric, it means they will react with both base as well as acid. So iridium and thallium are basic. And now the aluminium and gallium after boron, aluminium, gallium, their oxides are amphoteric, so they will react with both acid as well as base. However, iridium and thallium oxides are basic, and we know as we go down the group, electropositive character increases, and with the electropositive character, what we see, oxides becomes basic in nature. So reactivity towards acids and alkalis. So boron uh, doesn't react with acids and alkalis even at moderate temperature. This is what we see. The boron in the elemental form doesn't react with acid and alkalis. Aluminium dissolves in mineral acids and aqueous alkalis and thus show amphoteric character. And amphoteric character that just now we have seen, it dissolves in both mineral acid as well as alkali, means the acid as well as base. So aluminium, when it dissolves in the dilute HCl, it liberates dinitrogen. So this is reaction we know. So aluminium, it's electropositive metal. It's a metal plus 6 HCl aqueous, and what does it do? It replaces hydrogen of the HCl. So this hydrogen, it will reduce this hydrogen. So these two aluminum will give two electrons to two hydrogen and one extra electron to another hydrogen. So what we see on balancing, I'm sorry, this reaction, you see two aluminum atoms react with 6 HCl aqueous molecules, and these molecules aqueous means H plus and Cl minus ions will be there. It gives two aluminum 3 plus aqueous ions plus 6 Cl minus ions. So this is AlCl3 plus 3H2O. This AlCl3, we know AlCl3 also reacts with this reaction we have seen. AlCl3 acidified aqueous solution forms this. So if the acidified aqueous solution is there, that in the case that we see here in this reaction, acidified aqueous solution. So aluminum 3 plus aqueous is what? So 6 water molecules will be there binding with the aluminium, so coordinating with the aluminium, and 6 Cl minus will be free in the solution aqueous, and 3H2O gas will be liberated. However, what we see, concentrated nitric acid, though aluminium provides hydrogen with the HCl, but in the case of concentrated nitric acid, renders aluminium passive by forming a protective layer of on the surface. So with the nitric acid, aluminium reacts and a protective layer is formed, and thus further reaction stops. Aluminium also reacts with aqueous alkalis and liberates dihydrogen. As that we know, aluminium being amphoteric in nature, it can also react with the alkali base. So aluminium reacts with NaOH and plus 6 water molecules, the aqueous NaOH, and we see the high liberation of hydrogen in this case as well, and liberation of hydrogen plus the formation of sodium tetrahydroxoaluminates. This is tetrahydroxoaluminate. Aluminate is what? The anion, and tetrahydroxo group is there, and aluminium forming anions, so aluminate, and the oxidation state of aluminium here is plus 3, so plus 3 is shown here in the bracket. Now if you look at the reactivity of the group 3 metal with elements with the mm, halogens, they are elements. Boron is not metals, others are metals. Boron is metalloid, we have seen, it's more closer to a non-metal. So these elements react with halogen to form. So all the group 13 elements react with the halogen to form trihalides. Only exception is thallium iodide. Thallium triiodide is not formed. So other than that, we can see the formation of this element trihydride. So this element, suppose E is group 13 element. When it reacts in the solid state with the halogens 3x2, it forms 2ex3, and this is the trihalide compound of the group 13 metal. So now if the question is given, why what fumes appears around the bottle of anhydrous aluminum chloride? So anhydrous aluminum chloride we have seen. Anhydrous aluminum chloride, when we are talking about, means there is no water. And when there is no water, then why the fumes are being formed? The reason is anhydrous aluminum chloride in the water also exists as a vapor into the atmosphere, and water exists in the neutral form, and it is not acidified solution. And as we have seen in the case of what, if the solution is slightly acidic, then what will happen? Usually, if you, let me explain it with this example. Yeah, what is the trihalides on hydrolysis in water? It's a neutral water. It forms MOH4 minus. So even aluminum chloride, when it reacts with the neutral water at pH 7, it forms AlOH4 minus. And AlOH4 minus, we have seen this formation here. AlOH4 minus. The tetrahydroxoaluminate also forms here. However, if the solution is slightly acidic, what we will see, These OH minus ions will be neutralized. So this H plus ion will go and react with this. So in the slightly acidic solution, what will happen? So these water molecules will be there. This OH minus will be neutralized. So the water will now coordinate with the aluminium, not OH minus ions in the slightly acidic solution. So what we were seeing here is, uh, so if anhydrous AlCl3 bottle is kept there, so nearby in the atmosphere, some of the AlCl3 molecule will react with the moisture or the atmospheric moisture, and so this reaction AlCl3 plus 3H2O from air, it will happen AlOH thrice plus 3HCl. If the water is in enough amount, so this will what AlOH 4 minus will also be formed, can also be formed. So this AlOH thrice is the water, because the air water is not in very high amount. So this AlOH thrice is formed, and this AlOH thrice is white in color, and thus white fumes appear around the bottle of anhydrous aluminum chloride. Now let us look into the important trends and anomalous properties of boron. So what we know, the trichlorides, bromides and iodides of all these elements being covalent in nature are hydrolyzed in water. This thing we have seen. The species like tetrahedral MOH4 minus, this is the tetrahedral, we know sp3 hybridization, and octahedral MH2O6, this kind of formation we have also seen for the aluminium. And here is the hybridization is sp3d2, and the octahedral complex, this is a tetrahedral, this is octahedral, except boron. Then for the boron, this kind of formation will be not there, because boron doesn't have empty d orbital and boron doesn't have empty d orbital. It means it cannot form this H2O whole 6. This exists in aqueous medium. This kind of both the kind of compounds can exist in the aqueous medium. The monomeric trihalides being electron deficient, so trihalide monomeric, we know BCl3 is the trihalide monomeric, being electron deficient, and they are electron deficient, they have only 6 electrons, are a strong Lewis acid. This thing we have seen. So boron trifluoride easily reacts with Lewis bases such as ammonia to complete octet around boron. And so boron, the BF3 is a Lewis acid. It easily reacts with the ammonia, which is a Lewis base, which has a lone pair of electrons. And so this kind of adduct formation or the complex formation happens. And so in this case, what happens, boron will get its octet, because nitrogen shares both of the its lone pair of electrons, means one lone pair means the 2 electrons. With the boron, it pushes it into the empty p orbital of boron. So boron will also obtain 2 electrons from the nitrogen, and so the octet of boron will be complete in this complex, and the nitrogen is not completely losing the control of these 2 lone pair of electrons. So those lone pair of electrons will also considered to be belonging to nitrogen. So nitrogen's octet is also complete, boron's octet is also complete. Sometimes if this kind of complex formation happens, people show this BF3 minus NH3 plus. Sometimes people also show this kind of structure, because slightly positive charge will anyway generate on nitrogen and slight negative charge will be there on the boron, because the nitrogen, that lone pair, is being pushed towards the boron. So due to absence of d orbitals, the maximum covalency of boron is 4, that we know. So boron, this kind of complex formation is not possible with the boron. Most of the other metal halides are dimerized through halogen bridging, and the most of the other metal halides we see the dimerizes. The aluminum AlCl3 trichloride we have seen, it dimerizes. The metal species completes its octet by accepting electrons from halogen in this halogen bridged molecule. So once the dimer is formed, the halogen bridged molecule is formed, that we have seen in the case of AlCl3 here. This is a halogen bridged compound. So this is a chlorine bridged compound. And so this chlorine is shared between 2 aluminium atoms. This chlorine is also shared between 2 2 aluminium atoms. Sorry, this chlorine is shared between 2 aluminium atoms. This is also shared between 2 aluminium atoms. And this way, because of the presence of lone pair electrons of the on the chlorine, both the aluminium gets its octet complete. And so this kind of formation, this kind of compound are formed, the dimers are formed, and the metal species, because of the formation of dimer, completes its octet by accepting electrons from halogens. in these halogen bridge molecules. Now this question is there. Boron is unable to form BF6 3 minus ion. Why? You have to explain. So the reason is boron doesn't have empty d orbital. So if it doesn't have the empty d orbital, so it cannot expand its octet. So if it cannot expand its octet, so maximum electrons that can be in the boron valence shell is 4. So boron can maximum form is Bf4 minus, not Bf6 minus, because to have Bf6 minus, two vacant d orbitals are also required, like AlF6 minus. Two and vacant d orbitals are also required, where one 2f minus can push its lone pair of electrons. So that is not there. So boron doesn't form this. So due to non-availability of d orbitals, boron is unable to expand its octet. Therefore, maximum covalency of boron cannot exceed 4. So it cannot expand its octet, and thus Bf6 3 minus cannot exist. So I'll stop here.